Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In this session, we are going to continue talking about the conservative field and how it simplifies things. So last time we were checking to see how we can check if a to see if a vector field is conservative. Today we say, okay, so what's the next step once we find out that? Don't do it unless you check. Okay. So let me rewrite the example. F. So this is example one. F equals 2xy cubed in the I plus 3x squared plus y squared. I'm sorry, times y squared plus cos y in the J. We say we already checked and we know it's a conservative field. And because of that, I can write it as delta F, where F is what we call the potential function. So this is called potential function. Someone is saying, so what? Why do we do more work? Yeah, because it would make our lives much more easier, as you will see. So, what do we mean by that? Remember, we call this portion M and this portion N, and this is f of x and y. So I want to find a function by integrating with respect to both x and y. So basically, I will take the integral of n with respect to x, so I will get some terms plus a constant, but this constant would be a function of y. Notice, it has to be, right? Because we only have x and y. And the y is constant with respect to x. So we don't know how it works. So, and then I'm going to take the integral of n with respect to y and compare and see. No, I'm not going to do that. I'm going to take the integral of m with respect to x and the integral of n with respect to y and take a union of both, as you will see. So easy. So let's start with the m dx. You see, it's so easy to integrate because x only integrating with respect to x. So the x becomes x squared over 2, the 2 and the 2 cancel, and you get x squared y cubed plus a constant that is a function of y, but I'm gonna ignore it for a second. And then I'm going to take the integral of n with respect to y. When I integrate with respect to y, the 3x squared is a constant. The y squared becomes y cubed over 3. The 3 and the 3 cancel, and I get x squared y cubed. Plus, the integral of cosine is sine y. Now, you can see that this term appears on both. So, I'm going to write f equals x squared y cubed plus sine y plus a constant. And this is the potential function. Uh, I'm going to set it equal to 0. You will see why probably later. And you say, okay, you did a good job, bravo. But so what? No, I'll tell you, so what? Suppose I want you to find the integral. The problem asks you to find the integral of f dot dr of a curve, and they give you the curve. It may be part of an ellipse, it may be a straight line, it may be whatever the case might be. It may be given to you in parametric form. I don't care. But you say, well, what? You said, I don't care? Yes, I don't care once I have the potential function. Because assume that C is any curve you can think of, but we started from the origin and went, say, 2.1 and 2. Remember what we did with the fundamental theory of integration, we would say that this integral is the potential function evaluated at the end minus the potential function evaluated at the beginning, and that's it. There is no integration. Notice otherwise, I have to parameterize that and call it t2t, right? And then get the derivative of that, which is 1, 2. And then write the f, all of this in terms of t, parameterize it. And then do the dot product between f and r prime. And then integrate. You see how many steps? But once you realize it's a conservative field, you can find this easily and substitute, meaning the trajectory is irrelevant. Did I go from 0, 0 to 1, 2 directly through a straight line or through a step of several lines or by means of an arc of a circle? It doesn't matter. The answer will always be the same. Substitute. So when I say f of 1 and 2 would be 1 square 2 cubed plus sine of 2 minus 0 square 0 cube plus sine of 0. Done. So the answer is 8, 2 cubed times 1 square plus sine of 2. That's the work done by the field on that particle. See how fast it is? Just to show you, I'm not going to show you that in the next problems, but just to show you, I could have said I will parameterize r of t to be 0 plus t I plus 0 plus 2t j. So r prime of t would be I plus 2j. Then my force, see how cumbersome that becomes. 2 times t times 2t cubed I plus 3t square 2t square plus cos 2t j. Let's clean it up. 2 cubed is 8 times 2 is 16 t to the fourth I plus 2 square is 4 times 3 is 12 t to the fourth plus cos 2t j. And then you get f of r of t dot dr. So the I stays the same because it's dot 1. So you get 16t to the fourth plus 2 times that. So 24t to the 4 plus 2 cos 2t. So the integral of f dot dr becomes the integral here. T goes from 0 to 1, from 0 to 1 of 16 plus 24 is 40 t to the fourth plus 2 cos 2t dt. I get 40 t to the fifth over 5 plus 2 sine 2t over 2 evaluated from 0 to 1. 2 and the 2 cancel. 40 over 5 is 8. So you get 8 plus sine of 2 when you evaluate t is at 1 minus 0 plus 0. So you get the same answer. But see how many steps you had to take. While here, it's one line. So that makes conservative fields very appealing. They are simple. They don't produce rotation. They are irrotational fields, but they are very easy to use if we want to evaluate a line integral along any path. I don't think we need to do all three. So let's do two of them, I think. let's do example two. Because of the time, I don't want to make it a very long lecture because it's the same. You can do the third one on your own and check. Um, I don't know how you check, but if you are not confident, you can email me or text me or leave a comment and I will try to get back to you as soon as I can. I'm going to write f as, oh, I was going to write this as an example. Y z plus 2 I plus xz plus 2x plus 4j plus xy plus 5k. We know that it's conservative. Again, I keep repeating myself because I don't want you to assume that the field given to you is conservative without checking. You may get a completely wrong answer if you do that. So this is m, this is n, this is p. So let's take the integral of m dx. It's the integral of y times z plus 2 dx. All of these are constants, so I get xy z plus 2. Of course, plus a constant in both y and z. Then I'm going to do integral of n dy. It's the integral of xz plus 2x plus 4 dy equals xyz. Notice that this is xyz plus 2xy. So here is one term that is there. Plus, when I integrate with respect to y, I get 2xy. Oh, there is another one. Plus 4y, plus a constant in z. Then I'm going to take the integral of p dz, which is the integral of xy plus 5 dz equals xyz, again, plus 5z. So at the end of the day, you see how easy it is. My function is xyz plus 2xy. The ones that I underline, I write them only once. And then I have plus 4y plus 5z plus a constant. And this constant will be set equal to 0. And now let's assume I went from the origin again to point 1, 2, 3, just any numbers. And we want to calculate the integral along the curve of f dot dr. I say it's f of 1, 2, 3 minus the f of 0, 0, 0, which is 0, because when you substitute with 0, this is 0. So it's only f of 1, 2, 3. I will get 1 times 2 times 3 plus 2 times 1 times 2 plus 4 times 2 plus 5 times 3. And that's the work done. 6 plus 4 make it 10, plus 8 is 18, plus 15 is 33 work units. See how concise the work is? And just assume that I give you a curve. Well, if I'm nice, I will tell you, oh, our t is already parameterized as t2, t3, t. And notice here how you are going to add and multiply t's and 2t's and 3t's, and then take the derivative, which would be 1, 2, 3 multiplied by m and p as a dot product, and then integrate. Now in 3D, it's even worse than what we had in the previous example, right? So conservative fields make things much easier, and they have no rotational. We say the curl is zero. And next time, maybe we are going to take a step further and look at what is the relationship between the curve and the divergence. So when we say, I'm sorry, curl and diverge, I said curve, right? So the curl measures how your field is rotating in one direction or another. The divergence meaning if your field is going away as a source or coming in as a sink without. So the curl is about rotation and the divergence is about expanding or contracting. And you will see that a lot of that in electricity, probably in gravitation fields. And so anyway, we'll continue on the next session. I hope this one was short and not that demanding, so to speak, and it was easy to follow. If you have any questions, as always, leave me a comment in the comment section and I will get back to you as soon as I can. Otherwise, I wish you all the best and hope to see you soon.